A lot of the steps we'll be following in the simulation are quite similar to the static analysis of the truss, so I'm going to go a little faster. I'm assuming you've already watched the static analysis of a truss video. We're going to start by renaming the model to truss structure. Then we're going to create a new part which is 2D planar, deformable, and has a wire base feature. We'll set the approximate size to 10 again. Once again, we sketch out the truss using the Create Lines Connected tool as we did before. We then use the Split tool to split up the segments into truss members. And then we use the Add Constraints tool to identify the truss members that are of equal length. And then we dimension it using the Add Dimension tool. We create the new material steel with a mass density of 7,872 kilograms per meter cubed. A Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. We then create a new section called Truss Section and set it to type Truss. This section has the same steel material we just created and a cross-sectional area of 3.14 times 10 to the negative fourth. We assign the section to the entire truss. Then we move on to assembling. We instance the truss into the assembly as a dependent, which means the mesh will be on the part. This time we're going to create sets in the assembly. We're going to create two sets. The first one is the node on which the force will be applied, and the second one is the node at the extreme end of the truss structure where we're going to measure the displacement with time. To define a set, double-click on the Sets item in the assembly container. You get the Create Set window. Let's name our first set Force Point Set and click on Continue. At the bottom of the Sketcher window, Abacus prompts you to select the geometry for the set. Click on the node on which we plan to apply the force, and then click Done. Repeat the procedure for the endpoint set. Now it's time to define the steps. We're going to create a new step called Loading Step and place it after the initial one. In the static truss analysis problem, we selected a static general step. This time we're going to go with a dynamic explicit one. We can type out a description, and we're going to set the time period to 0.01 seconds. so our load will be applied over a very short time duration. Notice that NLGEOM, which stands for nonlinear geometry, has been turned on by default. Dynamic explicit analyses are often carried on in models where large displacements are expected, and nonlinear geometric effects can become important. Turning on the nonlinear geometry setting tells Abaqus to account for geometric nonlinearity in that step. We're going to leave the field output requests to the default pre-selected variables, so we're not going to touch the field outputs container. However, we are going to define history outputs in the simulation. So expand out the history outputs container. You see that Abaqus has gone ahead and created a default called HOutput1. Right-click on HOutput1 and choose Rename. We're going to name this history output request Force Point Output. Double-click on Force Point Output, you get the Edit History Output Request window. We do not want the domain to encompass the whole model, but rather point to the sets that we have defined. So in the domain dropdown, choose Set, and then choose Force Point Set. Set the frequency to every n time increments where n equals 1. We're not interested in the energy in this model. We would like to measure displacements. So disable the energy variable from the outputs, and instead expand out the displacement velocity acceleration container. We're going to choose UT, which stands for translations. Repeat the procedure for endpoint output using the endpoint set.